Hi everyone, I'll present our work of text-only training for image captioning using noise-injected clip. Please see our GitHub for collab notebooks where you can play with different variations of our model. So we will focus on the problem of image captioning, in which we get an input image and we want to create a descriptive text for that. Image captioning is a key task in vision language perception that requires both deep understanding of the visual worlds and high language abilities. There are many works on image captioning, but the problem is that usually they require large captioning datasets. And moreover, if you want to manipulate the style of the captions, you usually need to collect, again, new expensive paired data. So we suggest a solution for that, just not use images at training stage at all. Problem is, of course, how can we train a model in a level of understanding for image captioning without seeing even one single image at training stage? Obviously, we will need some proxy to images, and that will be the famous foundation model CLIP. So essentially, CLIP maps images and text to a shared latent space. So it has image encoder and text encoder, and it encodes images and text such that if a text describes an image well, its CLIP embedding will be relatively close to the image embedding. Now, on training stage, what we do is we take the frozen CLIP encoder of text and we train our text decoder to reconstruct its original text from the text embedding of CLIP. So essentially, we don't use any image at training stage, and we only do text reconstruction to reconstruct the original text. Now, in inference stage, we hope that this text decoder will be able to also decode CLIP image embedding into descriptive text. So what we actually do, we take a given input image, we encode it with image encoder of CLIP, we get its CLIP embedding, and we decode it using our text decoder that was trained on text only. So unfortunately, this naive implementation performs poorly. It usually gives you some caption that relates to the content of the image, but it's not very closely related sometimes, and it's sometimes funny, as we can see in the example here. Now, we think that the reason for those poor results is that CLIP has some inherent modalities gap, and other works shows that as well, that the text embedding in CLIP are not really on top of the image embedding of CLIP. They are closely related, but they are not really on the exact same place in the embedding space. So we can think on this inherent modality gap as some sort of standard distribution shift, meaning when we train our decoder on text only, we can't expect it performs well on images because there is serious distribution shift between text and images. Now, in order to solve this issue, we suggest to use noise injection in order to compensate for that gap. So what we actually do, we use the exact same architecture as we saw before, but now we will add additive Gaussian noise to the text embedding in training stage. And we will hope that now our text decoder will be more robust to distribution shifts, such that at inference, when we use image embedding, it will create a nice descriptive captions also for the CLIP image embedding. Now let's see some interesting results of image captioning metrics as a function of the noise variance. So when we have higher variance, the noise scale is actually higher. It affects more. And what we can see here is that when the noise scale is too low or too high, the performance are pretty bad, are very close to zero. But there is very nice range in the middle when our results are very, very high. It actually looks almost like a fully supervised model. Now the question is, how can we estimate the optimal noise scale without using paired data? And what we actually want to do is to have the standard deviation of the noise to be semantically negligible in CLIP embedding. For calculating such a negligible difference in CLIP embedding, we use different paraphrases captions that belongs to the same image, and we calculate the max norm between their CLIP embeddings And this will be our approximation for a negligible distance in the clip embedding. And apparently this max norm is a very good estimation for the optimal noise scale. Now we tested our method using standard captioning datasets, MS-Coco of Flickr-30K, and standard evaluation metrics for captioning. And we compare our method to two other weakly supervised image captioning models. One of them is ZeroCap that use gradients from clip to update a language model to create a caption. And the other one is Magic that iteratively decodes a caption based on its matching clip score. Now note that ZeroCap doesn't use any sort of training data at training, while Magic requires textual data and is similar to our approach. Here are the results of MS-Coco and Flickr-30K. As we can see, CapDec improves the state-of-the-art results by a large margin, almost actually twice than the previous work. We tested it on cross-domain captioning when we train on Flickr and test on Coco and vice versa, and we see that also here CapDec performs pretty well. We evaluated CapDec on style-guided captioning, and for that we used a dataset that has annotations of captions in romantic style and humorous style. And for that, we first pre-trained CapDec on pairs of image and text using clip image encoder, and then we fine-tune its style only on the text of the styled captions. And again, as can be seen at the third line, CapDec outperforms the state-of-the-art by a large margin. There are a few examples of CapDec that was trained on that data. You can see that it both related to the image and preserves the style. We were interested to see how CapDec performs when it trains on open text, meaning we can just take a book or a play or news articles and we can train CapDec to reconstruct that text, and then we can check how it works for image captioning. And we will show here two examples of that. I think it's very interesting to see that CapDec is still able to be related to the content of the image and preserve the style of the corpus. For example, here we can see that it gives, for Harry Potter, it gives the cat the name of Crookshanks, which is Hermione's cat. Now, maybe the most interesting extension of CapDec is to eliminate the need of captions at the training stage, using sort of artificial captions that will be built using text templates and a list of nouns, verbs, and so on. Well, that's it. Thank you very much.